Christopher, that one. Go.
It's like learning way more.
What you got here?
And so we were just sort of Thanksgiving Day. My vision was
How's life? How's the cat? How's the dog? How's everything?
This is terrible. We need to record this and upload afterwards. Okay, just record it.
Because that's streamed right now, so I'll be recording this.
Yeah, stream with that. When afterwards we'll override the stream with that. Okay. After the class is done, I need the SD card back. Take it to Yeah. Well, this is the one because there's let's go. So we should talk about the topics.
Right, guys, we're going to begin. A quick announcement before we start. Some of you may have seen we go through some Canvas. It's going to deal with state-bound learning and the perceptron algorithm. My hope is that we'll finish state-bound learning, or at least the theory part of it today, and we'll be able to get started with perceptron today. By Thursday, we'll have enough. We have covered enough that you can start implementing stuff, but by today you'll be able to start thinking about the second question and maybe the third question also, second and third questions. Just same things about this homework as I said about the last one, namely it could be time consuming. So I suggest you finish off the logistical, you finish off the theory part of this soon, and also software, the programming part, because we've not yet covered perceptron, I would like you to try getting done with all the data reading and making sure that everything is in a vector kind of format and things like that, just so that when we see the algorithm, we can implement it quickly. Any questions? Has anyone started this thing? Oh wow. Questions or started? Okay, questions.
So one of my questions involves the data.
Right.
So I'm going to say this wrong, but each vector doesn't contain all of the features. Is there a
Say that again. Each vector.
Every vector doesn't contain all of the features.
Right.
So I'm assuming that's more like something we'll see in everyday life where we don't have data for every single feature, and we wouldn't want to because it's just
So this
what's
would,
data.
yeah, so there are two separate things that are getting mixed here in what you said, and I just want to separate these out. And what you said applies to both. Point number one is, of course, in real life there will be certain situations where we don't get some features. Imagine that the features are coming from some sensors that are placed on a volcano, and the volcano destroys the sensors. We still need some information, so we make do with what we can get. So there are times when we will not have features and we'll have to approximate it somehow. We could infer some feature values by guessing the averages or something like that. In this particular data set though, and in this particular format, what's happening is, that's not what happened. In this particular format, the idea is that we are dealing with sparse vectors, namely Imagine a huge vector, which is, let's say we have 10 numbers. Okay, there are 10, this is a 10-dimensional vector, most of it is zeros. As a representational shortcut, just as a way of representing things, this particular data representation format has chosen to not represent zeros. So this is exactly the same as saying, let me just put some indices here, this is 0, 1, 2. So this is exactly the same as saying 5 colon 7. And this is the format you see. So it's not that the missing features are unknown in this particular data format. It is that this particular data format has chosen to represent only the non-zero features. Another way of saying the same thing could be this particular data format, you assume that everything that's missing is zero. Right? And when you're implementing your algorithms, you might want to, one of the decision choices you might have to make is, do you want to store in memory the entire vector like this, or only the non-zero entries like this? For example, if you choose to store the entire vector, this could be something like an array, or a NumPy vector or something. This could be a map, or a dictionary. Now, which of these you will choose to use to represent depends on other factors. For example, the thing on the array representation is going to work pretty well if you have small enough arrays. But imagine that the array dimensionality is 100 million, and the number of non-zero entries is 3. Why do you need to represent 100 million zeros? So these are kind of decision factors you have to, decisions that you have to make when you're implementing things. Today there seems to be a trend towards the array or the NumPy vector kind of representation, just because the hope is you can throw it at a GPU and make it work. But even with a GPU, you cannot load 100 million numbers or a billion numbers because they don't have enough memory, so you have to play all these things. The bottom line here is that you still have to make programming decisions. But you completely gone past away from your question, but was your question asked?
That was exactly my question.
Yes.
Which one do you pick?
Right.
That
Yeah. Okay, cool. Other questions? Another important announcement concerns office hours. Thanks to some optimizations that were forced on us. All office hours will be in this room here, MEB 3515. I sent out this announcement on Canvas also. All PA hours, my office hours will be in my office. This room is, I can tell you this is the hardest room to find in MEB. It's in a corner. The first time you look for the room, prepare to spend a minute or two going around the building. I can tell you that my first time I had to look for this round, I had to use that first search. So anyway, so there's that, and then because of this change, we had to change the times for 4 of the office hours. Just minor changes, and the details are on the website. You don't need to write this down unless you care about it. Okay? We do make use of the office hours. One of the reasons we decided to go to this sort of a conference room for office hours is for the assumption that many of you will be in office hours and taking advantage of this, and the TAs really would like to meet people. So, they do take advantage of these things. This is a conference room that can seat about maybe 15, 20 people at once, and whiteboards everywhere and all that. Okay? Any questions about this? I suspect this is just information. There's no question here. And you don't need to remember these numbers. These times, it's on the website and I sent out. We're going to continue with mistake-bound algorithms. In the last lecture, we looked at the idea of mistake-bound learning. And the idea is rather simple. we make no assumptions, or we looked at online learning, and the idea is rather simple, or at least the setup is rather simple. The analysis could get complicated. The setup looks like this. There is a sequence of examples that keep coming to the learner. The learner can choose to store whatever it wants, but it does not. It can at any point only access one example at a time. And you can think of online learning as this sort of a game that the learner and nature play. The learner gets an unlabeled example. It has to make a prediction on that example using whatever hypothesis or hypotheses it has. And once it makes a prediction, once it commits to a prediction, the true label is revealed. At that point, the learner gets a reward or gets punished and can choose to update its internal state based on whether it makes a mistake or not. So this is pretty much and at that point it throws away the example and it's ready for the next example. Now we came across this sort of a modality for learning in our attempt to quantify what does it mean to learn. A simple framework that we have is called the mistake-bound model. In the mistake-bound model, this particular sequence of events, this particular these three or four steps happen infinitely over time, and then the learner keeps track of the number of mistakes it has made, and the learning algorithm is called a mistake-bound algorithm for a concept if the number of mistakes that's made is only polynomial in the dimensionality of the problem. A concept is called a mistake-bound. A concept is said to be learnable in the mistake-bound model if there exists a learning algorithm. We may not know what the learning algorithm is. Maybe the proof only says there exists a learning algorithm that can learn this algorithm, that can learn this concept in making only a polynomial number of mistakes. So a concept, an algorithm is called a mistake-bound algorithm for a concept if it makes only a polynomial number of mistakes in the dimensionality. A concept is called mistake-bound learnable if there exists a mistake-bound algorithm for that concept. Okay, so this is the framework that we were looking at, and at the end of the last lecture, I mentioned that I can get to define whatever I want. I can call an algorithm mistake-bound. That doesn't mean there exists any mistake-bound algorithm. And what I started thinking about is, we started looking at this question of, can there exist any mistake-bound algorithm? Is this like just a made-up definition, or are there any mistake-bound algorithms? Of course, I said there are mistake-bound algorithms, but as a proof of concept, I want to introduce you to this algorithm called the halving algorithm. But before halving, I'm going to talk about another algorithm that we saw in the last lecture called fun, and this is the last thing we saw, so I'm going to repeat this. Let's say we have a finite concept class, and this, you will see very soon, this becomes important. Let's say we have a finite concept class, and we don't have access to the true function, but we know that the true function is inside this concept class, that's f. Our goal is to learn it. We'll look at this algorithm called con, short for consistent. What it does is, at any step, you remember I said these kinds of algorithms, they get to keep their own internal state. They can store whatever they want. This algorithm, what it stores is every function in the concept class. It starts off with just a list of all the functions in the concept class, and it sees an example. When it sees an example, what it will do is it will choose one of the functions it has in its memory randomly and make a prediction. And if that prediction is wrong, it will discard all functions that would have made an incorrect prediction. Right? So you could have had the concept class consists of say 4 functions, f1, f1, f2, f4, and then what will happen is a new example comes in, x, and it chooses to use f2 because it picked f2 randomly, and f2 makes a prediction. Let's say f2 says plus, and then nature reveals that the true label is really minus. So this is a mistake. At that point, the algorithm will enumerate all these functions, go through all of them, and remove every single function that would have made a mistake. So maybe f1 also would have said plus, and what has happened is now the set of consistent functions are only f3 and f4. Only f3 and f4 are consistent with all the examples that were seen before. And now it waits for the next example. Make sense? Yeah, I drew this picture here just to kind of illustrate the thing, but the most important point here is really that at any step, at any stage of this algorithm, whether or not it makes a mistake, the resulting set of functions is less than or it has fewer Ci plus 1 is either a subset or is equal to Ci. Either it has removed some functions because they made mistakes, or it did not make a mistake and it just didn't make any edits. So it's a subset, or it's exactly the same as Ci. Now this means that, keep in mind, we don't penalize the algorithm for not making mistakes. Our goal is only to count the number of mistakes. So the number of times it becomes a subset is exactly the same as the number of mistakes it made. So every time a mistake is made, at least one function will be removed because we know that there was at least one function that made a mistake. So that means Ci plus 1 is the number of functions in Ci plus 1 is strictly less than the number of functions in Ci every time there's a mistake. As a result, we count this as progress. We are kind of narrowing down on the true function. The number of consistent functions keeps reducing every time a mistake is made, but we believe, for some reason, we know that the true function is in C, which means there must be at least one function that is infinitely consistent, that's consistent with every example. It is the true function, which means we will end up removing at most the number of functions, at most all functions but that f. So learning is done when we remove everything but f. So we have one thing left. So the number of mistakes this thing makes is order of the size of the hypothesis of the concept class. Yes?
What if we never see the necessary examples to distinguish between some functions?
We've not made mistakes, so there's no penalty.
Okay.
So that's the thing. It's possible that we never see, let's say there are two functions f1 and f2, or in that case f3 and f4 that I saw. Let's say you had two functions f3 and f4. Let's say f3 was the true function. But we never saw that one example that would have killed off f4. Let's say we never see it. So what? You never make a mistake. So in all other examples, f3 is consistent, so life is good. Yes?
What if there's a noisy data and they remove the actual...
Yes. So I'm not assuming, I'm assuming that we don't have noise for both this one and halving. There's a very interesting analysis of these things in the case of noise. In fact, the idea of exactly that thing where you have functions that occasionally, you can think of the functions as making mistakes or the data as being noisy. That line of thought led to a very, very cool algorithm called the weighted majority algorithm. Unfortunately, we'll not cover it because it's not fashionable now. But this is one of these algorithms that keeps getting rediscovered every decade or so. We are due one. So, but that line of thinking leads to an algorithm called the weighted majority algorithm. And the person who did all this work, in fact, the person who defined this model of learning in his thesis, PhD thesis, was Littlestone, Nick Littlestone, and he's written a lot of. When he was a PhD student in the 1980s, he pretty much defined a lot of these things. Your homework question may or may not, one of your homework questions may or may not have been based on one of his papers. I think I just gave you a hint. Alright, so now one of the problems is all I showed was the number of mistakes this algorithm makes is the size of the concept class. Is this a mistake bound algorithm or not? Can you answer that question without extra information? Let me kind of refresh your memory. An algorithm is called a mistake bound algorithm if the number of mistakes is polynomial in dimensionality. Is that the same as being what I've written here? Yes.
Can we establish some relationship between the dimensionality of the features and the concept class?
One of the advantages of being a teacher is I can throw back the question at you. Can we establish a relationship between the dimensionality and the size of the concept class?
I don't think so from what we have right now.
Okay, that's really the question. That's the question. In order to make any statement about whether this is a mistake bound algorithm, you need to connect the dimensionality with the size of the concept class. It turns out for a lot of interesting functions we can. It turns out that, I mean, of course, in the limit, not necessarily, but very often we can. And at this point, we don't know for sure whether this is mistake bound or not. All we know is, so if you want to try to summarize this whole thing, the number of mistakes of this particular algorithm con is order of the size of the concept class. It's in the order of the size of the concept class. We still haven't decided whether it's polynomial or exponential or super exponential or anything. So for now, that's pretty much what we have. But we can still ask, can we do any better? Can we do any better than order of the size of the concept class? And the answer is yes. And this is roughly where we are starting today's lecture. The answer is this is the halving algorithm gives you an algorithm that is always, in the worst case, better than the previous algorithm we saw. Once again, the setting is the same. We have a concept class C, and we want to learn a known function from that using these queries, using what do you call them? Not queries, using the mistake bound model. What you do is we, just like the previous algorithm, will construct a series of sets, each of them subsets of the other, and we will declare learning to be done when that set, the current set that we have has exactly one element. We initialize the set with the set of all possible functions. Namely, we initialize it with the concept class. In the beginning, this algorithm keeps a set of all the functions that it has, and learning ends when there's exactly one element at some round. Let's say the CI is the ith round where learning is over. Now the only thing left is to say how these subsets are constructed. We are playing the same game as before. This is the mistake bound model. So we see one example at a time. So let's say we have an example X that has just arrived. Now, for any sort of mistake bound kind of model, you need to decide on two things. You need to decide three things. You need to decide what is the internal representation that the algorithm maintains. We've already decided that it maintains a set of functions. Another thing you need to decide is how does this algorithm make a prediction when a new example shows up. And the third thing you need to decide is how does this algorithm update its internal representation when it makes a mistake. So we have decided how the initialization is, what representation is maintained. It's a set of functions. It's some set. And now when an example comes in, we need to decide how it's going to make a prediction using the set of functions. In the previous setting, what we saw was it picked a random function and said, I'm going to pick a random function, and this random function gets to bear the load for the entire set, and it gets penalized if there's a mistake. What halving does is it takes all the functions, and every single one of them gets a vote on whether the label should be plus or minus. If a majority of the functions in the current set say plus, it says plus, or 0 or 1, let's say. If the majority of the functions say 1, it says 1. If a majority of the functions says 0, it says 0. So what I've written here is this set here is just a subset of Ci, the current set of functions, that predicts 1. And if the number of functions that predict 1 among the functions that it currently has is more than the number of functions that predict 0, the algorithm says that this example should be true, otherwise it says false. Now, let's say it makes a mistake. The prediction is, let's say, at that point, after making the prediction, this is an online algorithm, after making a prediction, it gets the true label. And let's say after making the prediction, it finds that the prediction was not the same as true label, as f of x. What it will do is now delete all the functions that made a mistake, just like the previous one. Just like the algorithm con, it only keeps consistent functions. It deletes all the functions that were inconsistent with the current example, and hence with all examples so far, all mistakes so far. So the only difference between this algorithm and con is how prediction happens in this part here. Yes?
I have a quick question about the comp. So imagine you randomly pick a function.
Right.
And given an example, it makes a correct prediction. How do you update that?
It doesn't. This is a mistake-driven learning algorithm. It's not just a mistake-bound algorithm, it's a mistake-driven learning algorithm. Any sort of an update happens only when there's a mistake. When there's no mistake, life is good, we just don't do anything. There's no.
So I didn't hear of the conclusion. Is it mistake bound algorithm?
We will get to that in a while. Right now, all I know, right now, I'm building this up like a suspense novel, I just realized. Kind of a very strange suspense novel, but all we know so far is that con makes, the number of mistakes it makes is order of the size of the hypothesis class, of the concept class in the worst case. This is a different algorithm. We will compare con and halving, and my claim is that halving is always better.
So for the halving as well, when a prediction is right, it doesn't make an update.
No, it does not. This is, like I said, both of these are mistake-driven algorithms. In fact, all the mistake-bound algorithms we'll see will also be mistake-driven. Changes happen only when there's a mistake. If there's no mistake, we just move on. Yeah?
So what if we don't see an example that doesn't give a mistake for both, for any of the functions in the set we have?
We don't make
When
any
does
of
the learning end?
Learning never ends. This goes on forever.
Okay.
This runs forever. Keep in mind that we are only tracking the number of mistakes, and you're touching upon a question that's kind of, this is a subtle question. Is it enough for us to just count the number of mistakes? Think of it from the point of view of having an unknown function that we are trying to learn. We will have no way of knowing whether we got the real function or not, because the only surrogate we have is, have we made mistakes? If we don't make any mistakes, we believe that we have a good enough function. First you, then you.
So in this example, you have the possible labels as just in binary, 0,
Yes,
1.
yes.
If it's like a multi-class whatever label, then can you still have the same count as the halving algorithm, or does it devolve into count?
No, you can do something similar. That's an interesting question. Actually, you can almost do something similar because you can reduce multi-class problems into binary by kind of giving up some dimensionality. You get a polynomial change. We can take this offline, but it's good. Yeah. It is good.
So in the case where we actually predicted right, and we don't change anything about CI, are we throwing away valuable information that could prevent later mistakes? Because if they're inconsistent with this example,
Right.
we should get rid of those.
You could, yes, you could, and that will change that will give roughly the same order of magnitude number of mistakes.
Okay.
I think so. But when I did think about this at some point in the past, and I think I convinced myself it does not change in the big O notation.
Okay.
Yes.
So sorry, I may not be understanding something, but if the true function doesn't lie in the majority, are we? I mean, it's kind of piggyback on this question. Are we just completely throwing out something that is like how do we correct if something isn't in the majority? Like for example, in the first case, we have our set of functions in C happens to be in the majority. It's wrong.
Right. So you do throw away at least half the functions.
Right.
Right. On the other hand, if your majority is right, you throw away less than half the functions. I don't know if there was a question there. I don't know if I answered the question you had.
So the functions that you're throwing out, there is no chance that the true function lies in that half.
You never throw out the true function by this setup, because you only keep a function if it's consistent with the ground truth, and so you never throw out a function that is consistent, and the true function is always consistent.
By no noise.
Assuming no noise. Yeah. There was some other hand. Yeah.
With real world data where C could be pretty large, does it get costly to run through pretty much every app?
Yeah. In fact, I was going to mention that. I'm glad you brought this up. So think about implementing this algorithm. You have to keep a list of all functions. If I ever find out that you've implemented this algorithm, I'll be disappointed because you can't. This is a conceptual. This is just a proof of concept. It's a proof of concept without any regard to computational or space complexity. Yeah. And but it just tells us whether a concept can or cannot be learned in the mistake world, whether there exists a concept if you allow infinite space and infinite compute. Okay, now once again we can ask the same question about this algorithm. How many mistakes will this halving algorithm make? Not as a function of the dimensionality, but as a function of the size of the concept class, just so that we can compare halving and conv. So let's say that this algorithm makes n mistakes. Now, learning ends when there's exactly one element, which means after making n mistakes, it stops. That means Cn will have exactly one element because learning is over, or it's not going to make any more mistakes. So the size of Cn is equal to 1. Now, what we also know is that Cn was generated by taking another set Cn minus 1 and throwing away something from it to get Cn. So there was a set, let's call this Cn minus 1, and more than half of these things made a mistake. And that's why we removed this side, and we were left with exactly one thing. This is Cn. Right? So Cn was created because there was a mistake, and when there is a mistake, how could there have possibly been a mistake? The majority of the functions predicted the wrong label. And as a result, we discarded a majority of the functions, which means we threw away more than half the functions. What that means is the size of Cn is less than half the size of Cn minus 1. Does it make sense? Okay, but let's now worry about Cn minus 1. How was Cn minus 1 created? Well, it was created because there was a Cn minus 2 that made a mistake, and more than half of it was thrown away. So the size of Cn minus 1 is less than half the size of Cn minus 2. And we can keep going until we go to C0. There are only n steps here because there are only n mistakes, and we make updates only on mistakes. Which means at every mistake, we throw away at least half the set of functions we have. We go back all the way to C0, that means the size of Cn minus 1 is less than the size of C0 divided by 2 power n. But what was C0? How did we initialize the set? It was the set of all the functions in the concept class. So the size of Cn is less than the size of C divided by 2 power n. We can combine those two things and we get the size of C is greater than 2 power n, where n is the number of mistakes. I can take log on both sides, so log 2, the size of C is greater than n, log is an increasing function, which means n is less than log of the size of the hypothesis of the concept class. Right? So the halving algorithm will make no more than log of the size of the concept class number of mistakes. Questions? Yes.
I'm still trying to understand how this is different than the Kahn algorithm, which also could get rid of more than half.
It could get rid of more than half, but there is no guarantee that there's no guarantee that every mistake will force it to get rid of more than half. It's possible that every mistake will, there was only one offending function, and we accidentally picked that. And so we might end up, in the worst case, removing one function at a time because there's no guarantee that a mistake will reduce the size by a half. The mistake could reduce the size by exactly one function. And in the worst case, because we have an adversary, remember the mistake bound is an adversarial sequence of examples. And the adversary knows the function and it knows what you're doing and it gives you that one example that will force you to remove exactly one thing, one function at a time. So the only difference is whether you use this sort of whether the set of the functions that caused the mistake to happen was the majority class or not. That's the difference between Kahn and Haas. And those of you who've seen binary search, I hope all of you have seen binary search. This is essentially binary search over the set of functions. Yes.
So in the halving, the n mistakes is, so for n equal 1 is the entire functions that it gets rid of, not.
For n equals 1? Sorry, I didn't get that.
Okay, so if it makes one mistake, is it for the entire functions or for every function in the set that it got rid of?
If it makes a mistake in the halving algorithm, all the functions that made a mistake are thrown out.
So is that one mistake?
That counts as one mistake, yes.
Okay.
That counts as one mistake because that is basically one example. All this, so we count the number of, all of these things are specific to the algorithm. It could have made other choices, but like I said, there are three decisions you need to make in a mistake-driven algorithm. What is the set of functions? What is the internal state? How do you make a prediction? How do you make an update in the case of a mistake? And a mistake is just this one step here. So it's not like all the functions made a mistake. The system made only one prediction, and that prediction was wrong. Other questions about the halving algorithm? Yes.
So, but we're still throwing out things in every single step. We're just, it's guaranteed. It's not guaranteed to be more than half unless we've made a mistake.
Yeah. Yeah. We as a result, we don't end up throwing the canonical halving algorithm does not throw out at every single step. We could, but you will not throw out more than half. In the worst case, you'll throw exactly one. So that's like that's a linear thing that disappears in the log, so it doesn't matter. And that's the reason for that analysis that I kind of vaguely mentioned. Other questions?
Excuse me.
Yes.
I can't understand why the next step of algorithm will have less than half of the
Previous step.
previous.
So let's go back here. So I just went back here because there's more white space. Let's say that you have, I'm going to use an example to illustrate this. Let's say you have 5 functions. F1, F2, F3, F4, and F5. Let's say that a new example comes in, and let's say this example is x. And at this point, we should ask. It makes a prediction by asking all these functions. Let's say it says f1 says plus, f2 says plus, f3 says plus, f4 says minus, and f5 says minus. The majority is a plus. The majority is wrong, and it gets thrown out, which means it's by definition more than half. Yes.
If the majority is right.
If the majority is right, there was no mistake. There's no mistake, we don't count it. So we are only counting the number of mistakes.
So, majority is right, we still throw out what is not majority.
No, we just we make no updates. The this was a question that came up. If the majority is right, we make no updates. Because the halving algorithm, the canonical version, is a mistake-driven algorithm. It changes its internal state only if there's a mistake, and if there are no mistakes, it believes that life is good and moves on. You could come up with a different algorithm where if the majority is right, let's say the true label here is a plus, it removes f4 and f5. You could come up with that.
But I don't get the idea why you just keep.
Well, it's easy to analyze. Sometimes we do things because these are easy to analyze. Honestly, yes. I mean, if I had to implement, okay, I'll never implement halving because it's inefficient, but you could think of a variant of halving. Maybe that should be a good exam question. Where you can do this, and analysis becomes a little bit more tricky because you're not guaranteed that every set will shrink this, every update will shrink the set by at least half. Because when you don't make a mistake, you shrink the set by less than half, and then you have to do some worst case bounds become a little bit uglier. And we don't need it because the point has already been made, which is it's logarithmic in the size of the constant. So even without that extra step, we get this logarithmic thing, and I'm sure somebody has put the effort. Anyway, the main point I want to make is it makes a logarithmic number of mistakes. You could make it slightly smaller by doing what you described.
So I think the whole idea behind this is just to prove that this is a mistake.
Just to prove that the number of mistakes is log of the size of the consequence. I still haven't proved that it's mistake bound.
Okay, because it's polynomial in the dimensions.
No. This goes back to the same thing. It's logarithmic in the number of functions. We never note that the dimensionality is not here at all. This slide does not have anything about the dimensionality, it only has the number of functions. I'll give you a concept class later where this is not polynomial. Okay, so the halving algorithm, as you mentioned earlier, is hard to compute. You have to remember, you have to store all functions, so don't do this. But in many concept classes, in terms of the number of mistakes that can be made, the halving algorithm is optimal. For all Boolean functions, it turns out the halving algorithm is optimal in terms of the number of mistakes. And optimal is a very specific definition. It means for the most difficult concept in the class, for the most difficult sequence of functions, for the most difficult concept in the class of, in the concept class, for the most difficult sequence of examples that are presented to it, there is no algorithm that can make a fewer number of mistakes. For some concept classes, the halving algorithm is optimal. One of the very cool Nick Littlestone's paper from 1988 or something gives an example of a function of a concept class that halving is not optimal. You can take a look at that, or you can think about it to invent a function where that happens. In general, optimality is non-trivial. You don't have to worry about this, but generally what you need is not to guess the prediction based on the majority class of the functions, but you need to know somehow the expected number of mistakes in the future. And you need to make a prediction based on the expected number of mistakes in the future, which becomes an even more complicated thing to predict. Compute, because you need to know the distribution and all that stuff. So if you don't if this is just for those of you who are interested, you can take a look at that in the future at some other time. So all I showed so far is that there is a proof of concept algorithm that makes con makes order of the size of the concept class number of mistakes, and halving makes order of the log of size of the concept class number of mistakes. Now, this is all worst case. That's really important for you to keep in mind. This is all worst case. In practice, maybe halving or con can make much fewer. This is in the worst case. It will make these many number of mistakes. There may be certain concept classes where halving makes way fewer number of mistakes. So there is a homework question where I ask you what's the number of mistakes that halving makes or con makes. I can't remember. The answer is not exactly this. You have to actually do some thinking. You have to rederive the process and think about the particular functions I described. Yes.
So suppose, I mean, this may not be possible, but suppose you have three names, right? 1, 2, and 3. Those are like functions.
Right.
And certain times 1 and 2 agree on something and it's the right classification. The other time 2 and 3 agree on something and it's the right classification. So is that part of the algorithm, or like is that a property of how halving works? So you don't discard everything that's wrong if you classify it as correct?
You only if the true function is not changing, if it's deterministic, that there's only one correct function and that function is always right, that will never get discarded. That's an invariant that halving has. That's pretty much the only thing that we can guarantee. Any function that is, the other invariant it keeps track of is any function that is consistent with all examples seen so far, it would never get discarded. Those are the only two things that we can guarantee. Okay, now let's look at some examples. All I said was, I framed this in terms of number of the size of the concept, I framed all these results in terms of the size of the concept class. We need to see what it means in terms of the dimensionality. Yes?
I was just thinking about something. You realize that if there's a mistake in the case of a con, how the update is done, like the end product of the update will definitely be the same as the end product for the update.
That's exactly right. The update is identical. The only difference is the prediction. Yes. Okay, now let's look at a set of functions. This is a set of functions that we saw before, conjunctions. These are all functions of, let's say you have n variables. There are n Boolean variables. The dimensionality here is n. And these functions are all conjunctions without any negation. Let's say or it doesn't matter, with negation. Let's say with negation. So when I say all functions with negation, so you can have x1 as a conjunction, x1 and not as a conjunction, 2 is a conjunction, and so on. Now, the question for you to think about is how many conjunctions are there if you have n variables? Can you tell?
There's going to be n squared plus n.
So,
with the negations included in this class.
Can you prove this?
So this comes from Euler counting all the numbers from 1 to n, and there's going to be that many.
The proof is much simpler, but I think this is not quite right. You have way undercounted it, turns out.
What?
You have undercounted quite extensively. How many? Yes.
2 to the power n.
Another.
If you don't consider negations, if we consider negations 2 to the power 2n.
So without. This is another possibility. Anyone else? And then I'll show you the right answer. You were close though. What you said is almost the right answer. I'm not going to worry about plus ones and minus ones. Anyone else? Let me show you the answer. It's 3 power n, not 2 power n. consider negation. The way to think about this is, imagine, let's say that we have n slots. We're building a conjunction. I'm going to first put n slots and so on. This is slot number 1, slot number 2, slot number 3, 4, 5, and so on. In order to build a conjunction, let's think about how the function looks. Either the slot can be filled with the variable x1, or it can be filled with the negation of the x1, or x1 is not present at all. So let's just call that t. Either for slot number 1, there are 3 options. Either you can have an x1, or you could have not x1, or x1 is missing from that function. If x1 is missing, these are all the functions that x1 does not have. For x2, for the second slot, I can fill it with x2, or not x2, or something else, and so on. The decision that you make for x1 is independent of the decision you make for x2, which is independent of the decision you make for x3. You have 3 options for each slot, and there are n slots. So the number of possible ways of filling these slots is 3 power n. Questions about this? You will be doing this quite a bit. So, for all kinds of functions. And that's why if you don't have negations, you are right. If there are no negations, that means this option gets deleted. So you get only 2 options, 2 ways to fill a slot. Either the variable is present or it's absent. So there are 2 options for each slot. So the number of conjunctions is 3 power n. The number of conjunctions with n variables is 3 power n. And now we can ask, how many mistakes does halving make? Halving makes log of the size of the concept class, which is log of 3 power n, which is n log 3, which is 4 n. So halving makes only a polynomial number of mistakes. You can ask, how many mistakes does con make? It is order of 3 power n. Right? So for this class of functions, halving is a mistake bound algorithm, whereas con is not. What this means is this class of functions is learnable in the mistake bound. There is at least one algorithm, namely halving, which can learn the function in making only a polynomial number of mistakes. Halving is learnable in the mistake, conjunctions are learnable in the mistake bound. Monotone conjunctions are also learnable in the mistake bound because they only have 2 power n functions. So keep in mind that all I said was there is an algorithm that can learn it, but that algorithm was just downright lousy because it was inefficient. In order to learn conjunctions with a halving algorithm, you need an array of size 3 power n to start off with. And if you have 1,000 features, you need 3 power 1,000 size array. So halving is just a proof of concept. It only shows there exists the possibility of learning this under the mistake bound. There is no guarantee that we can actually do it in practice. In order to show that it's doable in practice, there is one more step. Somebody needs to invent an efficient algorithm for learning conjunctions. Right? So, does this make sense? Like, there are 2 parts to this. There is whether the concept can actually be learned only using making a polynomial mistakes. That's just the learnability part of it. And then there's the efficiency part of it. Does there exist an efficient algorithm that can actually do this, meet this part? Turns out for conjunctions, we've already seen such an algorithm. Maybe last lecture, we looked at this algorithm for elimination. This slide hopefully stirs up some memories, where we had a bunch of examples, this was for monotone conjunctions. All we did was just erase all the negative examples and took only those features that were present among the positives. At least for monotone conjunctions, the elimination algorithm is efficient. It actually meets the mistake bound. It makes exactly n mistakes. There are n features, it makes n mistakes. The elimination algorithm realizes the mistake bound that the halving algorithm promises. And the elimination algorithm is, of course, efficient. So, what we have here is a proof that monotone conjunctions are learnable in the mistake bound and they are efficiently learnable under the mistake bound model. Yes?
Doesn't the elimination algorithm that we use not take into account knots?
Yeah, so this was this version that we saw was for monotone conjunctions. There's a slight variant of it which works for conjunctions. If you provide extra information, it becomes the same thing. Namely, all you need.
The knots of each one or something?
Sort of. There are a few variants actually. Yes. Yeah, in fact, there's a good exercise. Try to find and update the elimination algorithm to work for negations. Okay, so that's that. Now let's look at another class of functions called k-conjunctions. Now k-conjunctions are, now imagine that you have n features, a million features. But I also, let's say I give you extra information. I tell you that the true function has exactly k features relevant. I'm not telling you which k features are relevant. Some k features are relevant and the true function is just a conjunction of those k features. What that means is there are some k features without loss of generality. Let's say that is x0 through xk minus 1. This set here is the only relevant set of features. The other almost million features are just there because we didn't know better. And the true function is really the conjunction of these k things. If you knew that, can you learn better? The way to think about that is how many k conjunctions are there? Once again, we have to ask the same question: how many k conjunctions are there? And I've already given the answer, but we can make the similar sort of argument for the number of k conjunctions. So, first of all, once again, it's a k conjunction, which means that there are k slots to fill. I have there are k slots, but each slot is not associated with a particular variable. So what we need to do is first, among the n variables that are there, choose k of them, and now we know that these k things are present in the function. So let's say x0 is here, or not x0. Maybe x15 is here, and let's say the set is x0, x15, x31, and some other things, k things. And not x15 is here. This slot is for x31 or not x31. For each slot, you get two options. Either that variable is present or it's negative. And there are only k slots. We've chosen the k things. So, how many ways can you choose k functions, k variables out of n things? So let's n choose k. And once you have chosen them, you can choose to. We have the option of either negating that variable or not for each one of them. So it is, you have two options for each thing. So you have 2 power k. This is the number of k conjunctions that can exist. N choose k times 2 power k. You have k slots. First you choose the k things that should be there, and then we decide to add the negations one at a time. So once again, we can ask, how many mistakes will the halving algorithm make on this class of functions? So in the worst case, it will make log of n choose k times 2 power k. Now, because we don't care about constants, we can make an approximation of n choose k. N choose k is just it's kind of ugly to take the log of. So instead, we are just going to say this is definitely less than log of n power k times 2 power k. Right? For sure, n choose k is less than n power k, which is order of k log n. So for k conjunctions, the number of k conjunctions is n choose k. I wrote that as c n k because I could not get the brackets in and put everything in here. So the number of k conjunctions is n choose k times 2 power k, which is very, very crudely you can approximate it as 2 power k n power k. You take the log of that, it's k log n. So the number of mistakes that the halving algorithm makes on k conjunctions is just k log n. N is the dimensionality. So the halving algorithm is ridiculously efficient in terms of the number of mistakes. All it has to do is make k log n mistakes. And this is worst case. Keep in mind, this is worst case. Always remember, this is just worst case. Maybe you can do even better, if circumstances are perfect. So in the worst case, the number of mistakes k halving makes is k log n. So now we can ask, is this a mistake bound concept? From the point of view of number of mistakes, of course this is polynomial. Log n is less than polynomial. So it is a mistake bound concept, but there's another question that becomes important. For conjunctions, we were able to show two things. There is the mistake bound that halving promises, and we had an efficient algorithm that could realize the mistake bound. That was the elimination algorithm. We can ask the same question about k conjunctions. What's an efficient algorithm that can learn k conjunctions? And that brings me to another important point, namely representations and how easy learning can be or not based on your representation. But are there any questions about k conjunctions before we move on to this point about representations?
So you're randomly choosing k out of n?
I'm not randomly choosing. I'm actually enumerating all possible ways of choosing k out of n. I'm counting the number of functions. I'm counting the number of functions. How many ways can you enumerate k out of n and choose k? For every enumeration of k things, how many ways can you assign the negations? It's 2 power k. All of these are mutually distinct, so you have n choose k times 2 power k possible functions. Yeah.
So you aren't given possible combinations, all you're given is k.
All you're given is k.
Okay.
Yes. All you're told is there is a k conjunction that is consistent with your data. In other words, you're told that the concept class is a k conjunction, and k is known to you. Yeah.
I might be wrong, but isn't there supposed to be a k squared log n instead of just a log n? Because you're taking the log of n to the k, not just n.
Oh yeah, it doesn't matter because k is a constant.
Okay.
We only care about the dimensionality. So yeah, maybe you're right. I'm for some reason I don't even want to think about it because k is irrelevant. It's just a log n that matters. Yeah. Yeah.
On your k conjunctions, why don't you have to worry about the third? So you did 3 to the n for the first one.
Yeah.
She did
2 power n.
2 to the
2
k
power.
on the next one.
Because in the original case, what were the three options? The variable is present, the variable is negated, or there is no sign of the variable. So present, positive, negative, absent are the three possibilities. Here, we've already, if it's not present, it's not even in the k things that are chosen. Okay, so let's talk about representations. This is an interesting, almost philosophical question. Suppose the class of functions, suppose you are told the true function that you have is a conjunction. You know that only to learn. It seems like a no-brainer. Of course it should. Then my search space is fixed. I search the set of conjunctions to find the true. This was the same elimination thing that this function is just finding a consistent function, but also want to find that is in terms of the number. This problem is NP hard. Also for disjunct. Care about the proof by searching the space of conjunctions. If you also have this extra criterion, namely the minimum number of attributes, which is truly messed up. What we will see is that even though that's not true, we can learn it efficiently if we explore the set of linear threshold units. Remember, the set of linear threshold units can express conjunctions and disjunctions and m out of n functions and other things. Essentially, what this means is we have a class of functions, conjunctions, and we want to learn this class. We know that the true function is here. We want to find it. In order to find it, our search space is a much bigger class of things. It turns out that because the bigger class of things supports real numbers, we don't have to deal with combinatorial issues, and we don't have to deal with combinatorial search, and we can search the largest space much more efficiently. This may be the most counterintuitive result. It's as if, or this may be the most counterintuitive thing we've seen so far. I'm hoping that by the end of the semester we'll have seen at least 3 things that are counterintuitive. If I know that the true set of, if I know that the true function is inside this set, there is some reason to believe that you don't want to search this set, but you want to search a much larger set that also contains this set. And that will be easier. Searching a larger set is computationally easier than searching the smaller set. Why? Because the larger set has real numbers in it. The smaller set is discrete. So combinatorial search can be harder. And this is a kind of phenomenon that shows up every now and then when we deal with combinatorial search spaces. Yes? So, the point of this is, even though we may have a more expressive class of functions, namely linear threshold units, the search becomes a little easier, and that takes us back to learning a linear threshold unit. We'll get there after I finish up the summary. A quick summary about the halving algorithm. It's a simple algorithm. When I say simple, I mean it can be written on the whiteboard or on a screen. It's a simple algorithm for learning a finite concept class. It stores a set of hypotheses that it keeps refining iteratively. At every step, it receives an input, it makes a prediction using the majority label, and if the majority label is wrong, it discards the majority set of functions. And the halving algorithm can make this. I want to correct this. Make this order of C, because it can make fewer number of mistakes. It's logarithmic in the number of mistakes it makes is logarithmic in the Bigot notation in terms of the number of functions that exist. This does not necessarily mean that it's a mistake bound, but once we know what its actual C is, we can count the number of functions. I showed you 2 examples. I want you to, as an exercise, think about the number of mistakes halving will make if the concept class is all Boolean functions. In order to do that, you need to count how many Boolean functions there are, and you can ask whether halving is a mistake-bound algorithm for all Boolean functions. It turns out it's not always optimal because optimality requires minimizing the number of mistakes in the future. You can do other things. We will, instead of completely removing examples that make mistakes, you can upweight or downweight them. So that removing removing a function is an operation that eliminates the possibility of bringing it back. Instead of removing it, you can just slightly increase or decrease its weight. Or maybe you can increase or decrease the weight of a feature. And that is the idea behind additive and multiplicative update algorithms that we will see right now, unless there are questions. I'm going to now move to probably one of the few learning algorithms that have shown up in popular press for since the 1950s. It's the perceptron algorithm. My plan now is to introduce the perceptron algorithm. Over the next lecture, we'll look at the details of the algorithm and we'll analyze its mistake bound. It turns out the perceptron algorithm is also a mistake bound algorithm. And in practice, if you ever have to use it, you'll be using one of the variants of the algorithm, and we'll look at a few of those. So let's look at the perceptron algorithm. The perceptron algorithm is an online algorithm. Online being the class of algorithms that I just described earlier, for learning linear classifiers. Just to remind you about linear classifiers, the input is an n-dimensional vector. We'll call that x, and the output is a single label. We'll use -1 and +1 for the labels. For the output, it's binary classification. -1 is negative, +1 is positive, false and true. A linear threshold unit is this device that takes the input and classifies it by taking the dot product of the input with the features, adding a bias, and taking the sign of the thing. If that dot product is positive, you predict +1, otherwise you predict -1. You've seen this before. You can pictorially draw linear threshold unit this way. I put this picture in here mostly because this is how some neural networks are drawn sometimes. You have, in this picture here, you have 8 features, x1 through x8. I have a constant feature 1, that's like the bias. Every feature is associated with a weight. And the idea is that when this node here, x1, the value is placed there, the information flows along the wire to the other node here with the sigma, and when it flows along the wire, it gets multiplied by that whatever is on the edge. So you get W1, x1 here, and here you get B because B is multiplied with 1. All these things are added up by the summation unit, and then there's another unit here at the top that takes the sign. This kind of a thing is called a computation graph, where every node represents some computation that's done, and edges represent information flow. We are all experts about the geometry of linear classifiers. A linear classifier, as the name suggests, is linear. From the geometric point of view, the linear classifier divides the space into 2 parts using a hyperplane, and declares one of these sides to be positive and the other one to be negative. So the linear classifier is just this thing. We looked at the linear classifier, we did not see any learning algorithms. Perhaps one of the earliest learning algorithms for the linear threshold unit is this thing called the perceptron. This was a paper that was published in Psychological Review in 1958 by Frank Rosenblatt. Early versions of that showed up in 1957 also. The perceptron was a probabilistic model for information storage and organization in the brain. Heavy stuff. And then immediately, like we're saying, we're talking about the kind of speed that shows up that happened only in the internet era, but this happened in 1958. The paper was published in 1958 and very quickly made it to New Yorker and New York Times. If you can't read what's written here, let's see what the New York Times says. The Navy revealed an embryo of an electronic computer that can that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. We're still talking about a linear threshold unit. Just keep that in mind. That thing that divides the space into two parts. The New Yorker talked about how it was implemented on this digital computer known as the IBM 704. This was 1958, before the transistor was invented, and digital computers looked like that. So it really made a splash. The perceptron algorithm was, like I said, described the way we know of it in this 1958 paper. Earlier, there were some papers in math journals that kind of essentially hinted at the existence of the same idea. And the goal is very simple. If I give you a stream of examples that keep coming in, the goal is to find the separating hyperplane. And it's an online algorithm, and it processes one example at a time. It sees an example, makes a prediction. If the prediction is wrong, it makes a correction, and throws away everything else. And the internal state it maintains all along the way is the weight vector. The weight vector that characterizes the linear threshold unit. So I'm not going to introduce the algorithm right now because we are truly out of time. But I do want to remind you that this kind of a hype exists even today about a different class of algorithms. And just be aware of that.